Okay, good morning to everyone. Am I audible?
Morning, sir. Yes, sir, you are audible.
Okay, so we will start with the class. Okay, so in the previous class, we have gone with the basics of inverting and non-inverting type of amplifiers that are made about by using the operational amplifiers. So here again we need to uh, implement different circuits that are used to have the mathematical operations and based on the operational amplifiers. Okay, so we will be using operational amplifiers to design adder as well as subtractor circuits. So we have already gone with the inverting and non-inverting amplifier case, so we will just have a recap. Okay, so in case of inverting and non-inverting, so in case of inverting we have got like the output was minus RF by R1 multiplied by the input voltage or the V in, or we can call it like VI that we have seen. So this was the output that we have got in case of inverting. So as it is inverting, the output will be negative of the input. Okay, so out here there will be a negative sign in case of inverting. If it is non-inverting, in case of non-inverting, the output was V output is equals to 1 plus RF by R1 multiplied by the input voltage. So this we have seen in the previous class. You can just refer the concept from the previous class. So once we know the inverting and non-inverting case, there the output is depending on like minus RF by R1. So this minus RF by R1 is here considered as the gain. So gain in case of inverting is minus RF by R1. Similarly, the gain in case of non-inverting is 1 plus RF by R1. So if we plot output divided by input, whatever the content will be remaining parameter, that will be your gain. Similarly here, V output divided by V input, that will be 1 plus RF by R1, that will be your gain. So the similar gain concept will be used further while designing the adder and subtractor circuits. So adder, if you want to add inputs, so adder is whatever output we are going to get should be addition of first input and second input. So this type of structure should be there at the output. Okay, so here whatever some gain may be there, okay, or there may be no gain. That means if gain is 1, this type of structure will be there. So output should be the summation of both the inputs or whatever number of inputs we are applying to the input terminal. So that will be your addition or adder. So this type of concept we need to implement. So the one of the circuit for implementing the adder is this one. So this is an adder circuit. So you can just see from there is a feedback. So feedback will be always from the negative terminal. Okay, and at the negative terminal itself we are connecting two different inputs, input 1 and input 2, and input 1 is connected with a resistance R1 and then it is connected to the inverting terminal. Similarly, input 2 is connected to the inverting terminal by an resistance R2 and the non-inverting terminal is connected to ground. So this is the structure of a basic adder that we can implement by using operational amplifiers. So with the help of this output equations, in case of inverting and non-inverting, we can just get the relation between the input and output. Okay, we can directly get the relation or we can derive also. So in case of derivation, we can just proceed. So this adder is also called summing amplifier. So we are going to implement adder or a summing amplifier by using operational amplifier. So in that previous analysis also, in case of inverting and non-inverting, what we have assumed is, the assumption is, first one is, we are going to get like the gain or the closed loop gain, that is AV, or closed loop gain like ACL. So here we are considering like the closed loop gain is less, very less than the AV, that is open loop gain. So open loop gain, so here basically or we can just say like open loop gain, that is AV, is 10 to the power 6. That means it is like infinity. So if gain is very high, then we can use virtual ground concept. Virtual ground concept. So here we can use the virtual ground concept as the gain is high. That means we are considering here the operational amplifier is an ideal one. Then we are going to use the virtual ground concept. The second point we are going to consider is input resistance is infinity. So if this is the infinity, then it implies like I1 will be equal to I2 will be equals to 0. And in the first case, when gain is infinity, we are going to use the virtual ground concept. That means Vp will be equals to Vn, that will be equals to 0 because Vp is ground. So this is Vp and this is Vn. So Vp and Vn will be sorted, or it will be connected. Vn will be also connected to ground because Vp is ground. So that's why it is given here 0 volt. So once we are assuming these two concepts, 2 points, then we can proceed with the analysis similar to the previous one. So to analyze, we need to use the KCL. There are currents, so this is total current flowing through the RF resistance, and the current flowing through R1 and R2 will be I1 and I2. So if we are going to use by KCL, we can get like I total will be equals to I1 plus I2. This will be there. Now we need to find the IT. IT will be, it is showing the current direction this way. That means this is at higher voltage to lower voltage, there is a current flow is there, potential difference is there, so current flow is there. So this is at higher, V out is at higher, and this Vn is at 0, that is lower. So the current IT will be given by V out minus 0 divided by the resistance, that is Rf, will be equals to I1. Now I1 we need to find out. So I1 direction is showing this way. Okay, so if I1 direction is showing this way, so from this voltage at A terminal, A node, to this one, so A node is having 0, so 0 minus V input 1 divided by the resistance R1 plus I2. So again I2 we need to find out. So I2 will be again 0 minus V input 2 divided by the R2. Okay, so once we have got this, from there we need to just separate it out, the output with respect to input. So once we will be separating, we can get like V out will be equals to minus RF V input 1 divided by R1 minus, or it will be common minus will be taken, so it will be RF V input 2 divided by R2. So this will be the expression of the output. So from there we can see the output is here sum of V input and V input 1 and V input 2 with a ratio multiplied by RF by R1 in the V in 1 and V into RF divided by R2. It is a you can say constant parameter being multiplied. So that constant will be depending on the designer. If designer wants to have RF and R1 equal, then it will be giving out directly V in 1. Okay, so if we are going to consider RF and R1 and R2 are equal to R, if this is the case, then V output will be given by putting this, it will be equal to 1, and here the coefficient will be equals to 1, so it will become V input 1 plus V input 2. So this is the implementation of adder circuit. So here we are getting the output. So output is in magnitude, it is sum of two inputs that we have applied at the input only, but there is a negative sign, so that negative sign is because of the gain. So that is not a problem. We are just wanting to have addition of two inputs, so there we are getting the addition of two inputs. So this is the output in case of adder. So another case is here, this was the case when we have taken two different inputs. Now we are going to generalize the expression. So suppose we are having n inputs, so we input 1, we input 2, and so on, we input n. So there are n inputs, so there will be n resistances also, and there will be RF, that is feedback resistance, and again we will be proceeding with the similar analysis. By similar analysis, this is ground Vp and this is Vn. So if it is ground, it will be also a 0 volt. There will be no current flowing here inside the operational amplifier as input resistance will be high. So whatever current flowing through this feedback amplifier feedback resistance, the same current will be flown here also, and it is divided into different branches. So all the branches current will be adding together to give the current flowing through this RF resistance. So by using the KCL again, we will be writing the current equations, and then how the current is going to represent in terms of voltage and resistance, we will be representing that, and similarly we will be getting the generalized expression. So the generalized expression in case of n input will be V output minus, again here from there if we can consider like it is, again we are considering RF is equals to R1, all the resistances are equal to 1, equal to R, then we will be getting the expression like V input 1 plus V input 2 plus up to V input n. So I hope it is okay to everyone. So this is how we will be implementing the adder circuit. Up to here, anyone is having any doubt, you can ask. Okay, then we will be proceeding. So this is what we have got the output, but suppose output that we have got is having the relation between the input 1 and input 2, along with there is RF and R1, the resistances. So whatever resistances are there, if all the resistances are same, then we are getting the output that will be directly the sum of the inputs. So suppose we want to have this can be considered as like unity gain summer. This is a unity gain summing amplifier. Unity gain means here the output divided by input will be considered to be 1. So there is a unity gain. There is a constant. So the gain is here 1. That's why unity gain. Suppose we want to have a different gain. So to have a different gain, what we can do is here in this case we can just have like, if we are going to make, if R1, R2 and RF are not equal, then we will be utilizing the concept of like a non-unity gain. So non-unity gain means a gain will be there, and that gain will be non-unity. That means it will not be 1. So that will be decided by the resistances again. So RF is common. So RF we will be taking outside, and suppose R1 and R2 are equals to a constant value, that is R. In that case also we will be getting this type of relation. Okay. So if we are able to make, if suppose RF is 2 times R1, if this is the case, then V out that we will be getting is RF is 2 times R. So once we will be putting, it will be 2 times V input 1 plus V input 2. So this will be the relation. So this relation is non-unity. Okay, so it is a non-unity summing amplifier. Okay. So based on the value of resistances, feedback resistance and the resistance connecting the inputs, we can scale the output that we are getting. So this is non-unity summing amplifier. So this is how the adder circuit or addition we can do by using the operational amplifier. Next is an example. Okay, so this is an example of unity gain amplifier. So suppose this is the example. You need to find out the output. In this case, what will be the output? Just find it out. Yes, anyone? There are three different inputs. So input 1 is 3 volt, input 2 is 1 volt, and input 3 is 8 volt. And it is having the resistances, the respective resistances, and there is RF, that is this is RF, and we are getting the output. So what will be the V output in terms of V input? So the formula that we have just gone through, and even the concept of yes, what will be the output?
Minus 12.
Minus
12.
V output is coming out to be minus 12. Okay, anyone else? Okay, so from the analysis we can just see, like in the previous slide that we have just seen, if there are two inputs, this will be the relation. Okay, this is the relation. But if the RF and R1 and R2 all are equal, then the relation between the input and output will be similar to this. So from the circuit diagram we can just see the RF and R1, R2, R3 are all equal. That means the V output that we are getting will be equals to minus. So minus is because of the inverting. So minus, we will be directly adding the inputs. So input 1 will be added, plus 3 plus 1 plus 8. Okay, so that we will be adding, and as the RF and R1, R2, R3 are equal, the gain will be unity. So if gain is unity, it will be the output. So it is minus 12 volt. So this is how we will be calculating the output. So output will be, from there we can just see it is the addition of all the inputs with the gain, that gain is unity. Okay, so suppose one more resistance is connected with the same magnitude like 10 k ohm, and suppose here V input is 4, that is equals to minus 5 volt. Then what will be the output? If we are adding another fourth input, that is of minus 5 volt with 10 k ohm resistance, then what will be the output? Anyone?
Minus 7 volt.
Okay, so similar to the previous concept, again the output will be similar, like minus, we will be taking all the considerations, so plus 3 plus 1 plus 8, and here it is minus 5, so it will be minus 5. Okay, so by just calculating the inside 8, okay, it is 7, so it will be minus 7 volt. Okay, so I hope you have got the concept. So next one is non-unity gain amplifier. So this is example number 2. This was 1. So in this example we are having R1 and R2, okay, and R1 and R2 and RF. So R1 and R2 are same, 1 kilo ohm, 1 kilo ohm, but RF is 10 kilo ohm. So in that case, if we want to find out the output, so the output will be minus RF divided by, or we can just use the generalized or the actual expression. So it is minus, it was RF V input 1 divided by R1 plus RF B input 2 divided by R2. So by putting the values, so it is minus 10k, that will be taken outside, divided by R1 and R2 are equal, so it will be 1k outside, and V input 1 and V input 2. So V input 1 is 0.2 plus 0.5. So now 1k, once we will be dividing, it will be 10, so minus 10 multiplied by 0.7. So once it is multiplied, it is minus 7 volt. So the output from here is, we can get V output is minus 7 volt. Okay, so this is how we can calculate the non-unity gain adder output also with having different RF and R1 and R2. Okay, the next example, so by using the similar adder circuit, we can implement the averaging amplifier. Averaging amplifier means, if there are average, what is average? So average is total number of total, you can say, sum of all inputs divided by total number of inputs. So that will be average. So suppose there are 4 inputs, so all the inputs sum will be there at the top and divided by the 4 will be there and that at the down. So to implement that, what we need to do is, so by using the expression from there, we can just see from the expression, or from here we can just see, so whatever the RF by R ratio is there, that should be equals to 1 by the total number of inputs. So there are 2 inputs, so RF by R should be 1 by 2, then it will be an average output. If there are 3 inputs, so RF by R should be 1 by 3, then it will be become an average, the output will become an average. So similarly here, so there are 4 inputs, so we need to have the 4 inputs, means the RF by R, these R should be equal, and RF by R should be equals to 1 by 4, then we will be able to implement the averaging concept. We will be having the average. So with respect to here, V output will be equals to minus RF divided by all the resistances are equal. So that is R plus V input 1 plus V input 2 plus V input 3 plus V input 4. So RF is 25K divided by R. R is 100K. It is 100K. Plus sum of all the inputs. So we will be adding all the inputs. So 4 plus 3 plus 2 plus 1. So it is 7 plus 3, that is 10. And by dividing it, it is 1 by 4. So there are 4 inputs and it is 1 by 4. So it has become an average. So 10 by 4. Okay. So it is minus 2.5. So this is our output. So the output is the average of all the inputs. So this is how we can use the summing amplifier to implement the averaging amplifier. Similarly, another example is we can use the summing amplifier to implement the scaling amplifier. So scaling amplifier means there are 3 different inputs. We will be able to scale each input with a ratio. Okay. So here scaling means V output is minus, first one will be RF divided by R1 into V1, V input 1, plus second one is RF divided by R2, V input 2, plus RF divided by R3, V input 3. So this is the generalized expression. There, if RF will be the same in all cases, but R1, R2, R3 all are different. So if all are different, the ratio of this term, so this term ratio 1, 2, 3. So if all the ratios are different, whatever the ratio is there, this will be a coefficient. So if suppose sometimes it is 0.5 times V input 1. So it is going to scale V input 1 0.5 times. So whatever the coefficient is there, if coefficient is not equal to 1 in all the inputs cases, the particular input is going to scale down. So this is how we will be able to implement the scaling amplifier. So from there we will be able to scale the inputs and the output we will be getting is scaled version of the inputs. So this is the scaling amplifier implementation. Okay. So the next topic we will see is subtractor circuit. So by using operational amplifier, we can implement the subtractor also. So we have already seen how we can implement the subtractor. Like there are 2 different inputs. So in case of normal, the basic operational amplifier, we have got like V output is gain times the VI. So this VI was, this is the gain. VI was V input minus V1 minus V2, or with a difference of 2 different inputs. So it was V2 minus V1 was there. So by default it is implementing the difference. So that means by putting the 2 different inputs, add 2 different input terminals, like one at the inverting and another at the non-inverting. So by using this concept, we can get the output that will be a difference of these 2. So just we will be proceeding to solve it. So suppose we are having the inverting case. So here we can just divide because there are 2 different inputs are there and both are connected to at 2 different input terminals, that is inverting and non-inverting. So what we can do is we can analyze the circuit as a superposition theorem. So superposition theorem is what is superposition theorem? Anyone? Yes, anyone? What is superposition theorem?
So it is a theorem with the help of which we solve the circuital problems. Like we consider one source at a time, and we consider the other source deactivate, and we'll solve the problem.
Okay, yeah, sure, sir. So similar Yeah, the similar concept we need to implement here. So because there are two different inputs are there at two different terminals, one is inverting and non-inverting terminals. So what we can do is, by using superposition theorem, what we will be doing is we will be considering input 2 first, and at that time input 1 will be making 0. Similarly, the second case, what we will doing is V2 we will be making it 0, and we will be considering the V1. So with respect to V1, what we are getting the output, that will be output, suppose 1 is there, and if V1 is 0 and V2 we are considering, then with respect to that we are getting the output, suppose it is V2, V output 2. So at the final, what we will doing is final output will be addition of V output 2 plus V output 1. So this is what the superposition says. So if there are different input voltages or different voltages are there, so one voltage at a time we are considering, and whatever the circuit analysis is there, we need to do the circuit analysis, and then second input we need to consider and do the circuit analysis, and finally whatever the output we are getting we need to add. So that will be equivalent to analyzing the circuit by considering both the inputs to that circuit. So this is basically superposition theorem. So we need to implement the superposition theorem. So once suppose we are considering the V2, and at that time V1 is 0. So V1 is 0 means if it is connected to 0, if 0 is there and this is already open, because we are considering the virtual ground and input resistance is high, our input is infinity, so it is open. So if it is open, it is connected to ground, so there will be also a ground, it is ground, so it is 0 and it is 0. So that means this terminal will be overall connected to ground only. These resistances will not be having any voltage drop, so there will be no current flowing. So if V1 is 0, at that time it is 0. If this is connected to 0 by virtual ground concept, this will also be a 0. So similar analysis we have already done. It is similar to the inverting amplifier case analysis. So at that time the output, that is output 2 is supposed there. So output 2 at that time will be given by the minus RF by R1. So here RF is R4 divided by R1 is here R2 multiplied by the input voltage, so that is V2. So this will be the case if the first case we are considering. In the second case, if V2 is 0 and V1 is some voltage, okay, so suppose this is V1. Now in the second case, if it is having V1 and this is connected to 0, okay, if this is connected to 0 and this is V1, then we need to find out this value. So this will be VP, and whatever this VP is there, similar VN will be there by virtual ground. Whatever VN is there, VP is there, similar VN will be there. So here first we need to find out the VP. So VP we need to find out. Here V1 is there, so V1 will not be here, VP. Okay, so it is like a resistance, another resistance. So and this is V1 and this is R1 and this is R3, and VP is this value. This is our VP. So by using voltage divider we can get the VP. So VP will be equals to R3 divided by R1 plus R3 multiplied by V1. So this is our VP. So once it is VP, it will be equals to VN, and if it is VN, now we need to do the current KCL at this node. Okay, so suppose the current direction is this. This is the direction of current. So this is suppose current I1 and that will be current IF. So by using the KCL we can get I1 will be equals to IF. So we can get I1 will be, this is at high and this is at low because this is at ground. So Vn minus 0. So Vn minus 0 divided by the resistance, that is R2, will be equals to current flowing from here to here. So it is V output minus Vn, V output minus Vn divided by Rf, and Vn is nothing but the Vp itself. Okay, so by here we can get the value of V output. We need to find out the value of V output. So V output will be equals to RF by R2. See, RF is R4. RF is R4 itself. So we will be using the R4. So R4 multiplied by Vn divided by R2, and V0 is plus Vn. So from there we can get like it is 1 plus R4 by R2 multiplied by Vn, but Vn is nothing but the Vp, so it is 1 plus R4 divided by R2, and instead of Vn we will be writing this value, so it is R3 divided by R1 plus R3 multiplied by V1. Okay, so this is how the output is there. So this is the output relation in case of subtractor circuit. Okay, so this is the case when the second case we have considered. So this is case 1 and this is case 2. So this output, that output will be nothing but the output 1. So output 1 we have considered, so finally it will be output 1. So this is output 2 and this is output 1. So final output will be the output 2 plus output 1. So by adding these two, we need to get the final output. So final output will be the V output, that will be the addition of output 2 plus output 1. So by putting the values, we can get the V output. Output 2 is minus R4 divided by R2 into V2 plus 1 plus R4 divided by R2 divided by R2 multiplied by R3 R1 plus R3 into V1. So from there we can just see like V output that we are getting is in magnitude, just we can see it is V2 is negative and V1 is positive. So it is V1 minus V2, the type of relation is there, but there is some coefficients. So these coefficients are in terms of resistance. So this resistance, by putting the different value of resistance, we can get the resistance removed. So with respect to that, we will be getting the relation. So suppose if this is the relation, by putting different R1, R3, R2, R4, we can get the exact relation like V1 minus V2 type of relation we can get from this. Okay, so this is how we will be implementing the subtractor by using the inverting and non-inverting case of operational amplifier. So this was the first type of inverter, subtractor. Another way to implement the subtractor is this one. This is method 2. So in this method 2, you can just see. So in the previous we have seen is we have implemented the inverting and non-inverting in a single operational amplifier. Okay, so similar concept has been implemented with two different operational amplifier. So in the first case, input we are applying it at inverting terminal. Input is applied to inverting terminal. So whatever input we have applied, with respect to that there will be an output. So output is 1, suppose output 1 is there. So this output 1 is there, and in the second case again we are applying the input, okay, second input to this, and finally we are adding these two. So adding these two means whatever the inverting output we will be getting, that will be a negative value because it is inverting. So V output 1 will be negative. So we are making the negative first, and then this negative voltage and positive voltage are being added. This is an adder. So this is the first case is inverting amplifier, and in the second case we are making the adder amplifier or summer amplifier. You can just write it is summer amplifier. So first the step we can get is, first one is inverting. So inverting is there. With respect to inverting amplifier case, the output will be RF divided by R1. So that is gain multiplied by input. So input is V1. So this is our V output 1. So once we have got the V output 1, we need to use the summing amplifier case. So by using the summing amplifier case, the V output we can get is, by using the summing, this is V1 and V2. And there is RF, R3, R2. So it is minus RF into V1 input 1. Input 1 is V01 divided by the resistance, that is R3, plus the second input, that is V input 2. So in that case RF divided by resistance, that is R2. So this RF divided by this resistance with the input V input 2. Okay, so this is the V output. So from there you can just see, by putting the V01 value we can put here. So it is minus RF V01 is given by minus RF by R1 into V1. Okay, plus second term RF divided by R2 into V2. Are you able to get this point? Okay, so now it is minus, overall outside is minus, and this is minus term is there and plus term we will be taking first. So RF by R2 into V2, and it is minus RF into RF again. So RF square is there divided by R1 R3 into V1. So from there we can just see, so V output is minus times the V2 minus V1 concept is there. So by putting the value of RF and all of, suppose all the resistances are equal, suppose all the resistances are equal. So suppose if RF is equals to R1 is equals to R2 is equals to R3 is equals to R is there. If all the resistances are equal, by putting the resistances we can get V output will be equals to minus RF and R equal, which will be V2 will be remaining. If this is the R square, by putting the R here, R square will be there, so R square will be 1, so it will be 1. So this is how the output we will be getting if all the resistances are equal to R. So output resistance is the negative sign with, it is V2 minus V1. So it is doing the subtraction. So subtraction is being performed between the given two inputs. So this is one of the type of analysis to do the subtraction by using the operational amplifier. Okay, so in the previous one also we can just get the ratio, so that we will be implementing the output V output, so that will be the concept like V1 minus V2 type of concept will be there. Okay, so I hope you have got the concept, like how we are going to implement the subtraction circuit or subtractor circuit by using the operational amplifier. So we will now see some examples. So suppose this is an example 1. So in that circuit, the second method that we have got, so suppose there are different resistances are there. So this is RF is equals to 1 mega ohm. In that case, for this circuit, RF is given 1 mega ohm, R1 is 100 kilo ohm, R2 is 50 kilo ohm, and R3 is 500 kilo ohm. If this is the case, just find out what is the output relation with respect to input. So what is output? Just find out by putting RF this one R1, R2 and R3 values in this circuit. So just go with the circuit and put the values and let me know what is the output. Yes, anyone? Have we got our output?
Yes, sir.
Yes.
20 into V2 minus V1.
Okay. So our output we will be getting is 20 minus 20 uh, V2 minus V1. Okay. So by just putting the values into this expression also, this is the expression, or yeah, this is the expression that we have got. So by putting the values of different resistances, we can get the relation. So V output will be minus 20 times the second one, that is V2 minus V1. Okay. So okay, another example is there. Example 2 for the subtraction circuit. So just subtractor amplifier is there. So just go with the question and let me know what will be the output. The output will be in terms of V1 and V2. Yes, anyone? So one thing, like while
V1 minus
proceeding the
V2.
V1 minus V1
V2.
minus V2. Okay. So like while proceeding this, we need not to go again and again with KCL and all. Okay. So what we need to do is we just need to write the output expression in case of inverting and non-inverting case. So the output will be because of the inverting case and because of the non-inverting case. So what we will do is, so output in case of inverting, we already know it will be minus Rf by R1, minus Rf by R1, that is minus Rf by this one. So Rf is 100k divided by 100k is the R1 also, multiplied by the V2, whatever the input is there. So this will be the case of inverting. In non-inverting case, we need to find out this value. Okay, so we need to find out Vp. So Vp we can separately find it out. So this is 20k and this is 20k and this is our Vp and this is V1. So Vp from there will be 20k divided by 20k plus 20k into V1. So it is 1 by 2 V1. This is our Vp. Okay, so from there we have got the Vp in terms of V1. So in case of non-inverting case, the output that we will be getting is 1 plus Rf by R1. So Rf here is 100k divided by 100k. So this is gain multiplied by the input. So input is here Vp. So instead of writing Vp, we will be writing Vp in terms of V1. So Vp in terms of V1 is 1 by 2 V1. So from there that will be cancelled out. So it will be minus V2 plus, it is 1 plus 1. So that is 2 into 1 by 2 into V1. So it is V1 minus V2. So V output will be V1 minus V2. So here whatever the input voltage is there, V1 and V2, with respect to that we will be getting the difference of V1 and V2 as the output. Okay. So suppose V2 is equals to 5 volt and V1 is equals to 10 volt. So now we will just put the value inside it. So it will be V output will be equals to V1 is 10 volt minus V2 is 5 volt. So output will be 5 volt. That will be the difference of these two. So I hope you got the concept. So anyone is having any doubt till now, you can just ask. Otherwise we will close the class. Yes, anyone is having any doubt regarding the concept that we have gone, adder and subtractor? That is very easy chapter. So once we know the concept of operational amplifier, that will be very easy to implement all the concepts related to operational amplifier. That will be circuital analysis. So these are the application of operational amplifier. So just we will see some few more examples related to operational amplifiers into later classes. Okay, so this is summing amplifier and subtractor amplifier. Okay, basically addition and subtraction by using the operational amplifier. Also we have seen the averaging concept and scaling concept by using the operational amplifier. So operational amplifiers are used to implement the arithmetic circuits or arithmetic or mathematical operations. That's why it's called operational amplifier. So we are clearly able to visualize like how we are implementing the different arithmetical circuits. So thank you. Now I will be closing the class.
Thank you, sir.
Yeah, thank you.